Okay, so just to start, hi everyone, I'm Manya. I'm almost a PhD in theoretical physics at King's College London. Um, the topic I work on is, in particular, the quantum effects on black holes. So I guess from the start, I gathered many people are chemists. So actually, what I do is kind of work on the entropy of black holes. So if you're familiar with entropy from chemistry, that's my topic anyway. I won't be talking about that too much though. Um, the idea here is just to talk briefly about the kind of quantum effects on black holes. So before I start, I just really quickly want to say that so far in theoretical physics, we have two theories that work for our universe. One of the theories is the theory of kind of larger objects, which is like gravity and so on. The second theory is the theory of quantum mechanics, which explains the behavior of small particles, in particular using quantum mechanics. So in general, we don't have a combined theory, a way to merge both of these to get a full understanding of the universe. However, we can kind of study both theories and their limits to study things like the quantum effects on black holes. Okay. So the content for this talk, I'm going to start by just introducing what black holes are and talk about the different types of black holes. Afterwards, I'm going to talk briefly about what quantum mechanics is. I'm not going to go into that quite deeply. Just think it's a little bit of a quick overview of almost what we need from quantum mechanics in order to discuss some of the effects quantum mechanics would have on black holes. Okay. So first of all, what are black holes? So they're celestial objects, so they exist in the universe. They have a strong gravitational field, so strong, in fact, that nothing can escape, not even light. So in particular, the reason me and you and everyone here can see the moon, for example, is because light rays go from the sun, they hit the moon's surface, and then they get reflected and they fall into our eyes, and then we go, oh, okay, so that thing over there, that's the moon. But if the moon instead was a black hole, light rays would shine from the sun, but they would go into the black hole and they would never come out. So they would never be reflected off the surface and into my eye. So as a result, I actually never see a black hole, which is what gives its name in particular, because black holes look like holes that are black because nothing can be seen from them. So in particular, this is an artist's depiction of a black hole. The thing at the center is the black hole, the dark area. It's darker than the rest of the space around it. Basically, that's how you kind of detect a black hole. We'll talk about that a little bit more later on. Usually, a black hole is surrounded by a cloud of highly energized particles, and these energized particles are letting off loads of photons, which is what we see kind of around the black hole. Okay. It's gravitational force of just tearing them apart, and as it tears them apart, it energizes them and we see them. Okay, so this is just an artist's depiction of a black hole. So we have three types of black holes. The first type, somewhat the most exciting type, are primordial black holes. They're very relatively small mass, or they could be very large mass. In particular, we usually just assume they were smaller mass. They were around in the early universe. So how early would be before stars and galaxies even formed? So quick review of the Big Bang was just that after the Big Bang, there was quite some time when the whole universe existed in a much smaller amount of space. And in that small amount of space, all of the known mass that we see around the universe existed in this kind of plasma-like state. So within the plasma that you see in this artist depiction, some areas just congregated more and more mass and became kind of dense enough to become black holes. These black holes were called primordial black holes. In particular, we have not observed this type of black hole yet, particularly because it was around a really, really long time ago. So to find it now would be a lot of work. So they're actually theoretical, but within the theory of cosmology and gravity, they are 100% completely expected. There's nothing to rule them out from having existed back in those days. Okay. And nothing in particular to say that they did exist either, just that they theoretically can have existed. Okay. Any questions about primordial black holes? No? Okay. So the next type of black holes are stellar black holes. They're about the mass of a large star. Um, so their mass kind of gives away how they formed. They're the remnants of massive stars. Um, so in general, when a star such as our sun, but much larger than our sun, so about 10 times the mass of our sun, runs out of fuel, it can no longer have enough mass in its core, enough energy in its core. So what you get is the pressure of all the mass that's around the star kind of collapses. The outer layers shed off in a supernova, and the inner core just collapses in itself and becomes more and more dense. And as it becomes more dense, eventually it becomes a stellar black hole. This was the first type of black hole to be observed in 1971, and it was found because of its effect on a nearby star. In particular, the black hole was called Cygnus X1. What happened was you had a binary star system, so kind of like our solar system, except there were two stars in that solar system. One of the stars, the larger one, became a black hole. The second, and then sitting here on Earth, what we saw in 1971 was the second star was getting devoured by the black hole. So this is an artist representation of what was going on. So what we actually saw on Earth was just a star shrinking very, very rapidly. And it fit the exact mathematical model for what would be happening if it was a black hole devouring that star. So yeah, that's like a little artist depiction of what was going on. The first star dies and becomes a black hole and starts to eat its partner. So there was actually a lot of debate for many years. I think it was only settled like in recent years, 5-10 years ago, that it definitely was a black hole. In particular, famously, Stephen Hawking said that this is not going to turn out to be a black hole. He actually had a bet with one of his friends, which I encourage you to look up anyway, because it's a nice, funny story about whether or not this would turn out to be a black hole. Now we know for sure it is a black hole. Okay, so the next type of black hole is supermassive black holes. So this is genuinely a photograph, so enough artist representations. I can give you one photograph. This is a photograph of the M31 galaxy. So in particular, so Earth sits in the solar system, orbiting the sun, which is called Sol. That's our solar system. And then all of our local kind of stars all have these solar systems around them, and they sit together in the Milky Way galaxy. And similarly, then a little bit space apart, there's loads and loads of galaxies in the universe. In particular, this is a photo of a galaxy called the M31. So as it looks like a spiral galaxy. The thing everything is kind of orbiting is supposed to be a black hole. Now it's no longer supposed to be. We know for sure that at the center of supermassive galaxies sit supermassive black holes. So this was until very recently completely hypothetical. So supermassive black holes are the mass of billions of large stars. They're thought to have, we don't know exactly how they formed, but they're thought to have formed at the same time as galaxies. So initially how a galaxy forms is more and more mass collects in one particular region of space, and it looks like an elliptical shape. And then it kind of gets shape because whatever is at the center of this ellipse gets more and more mass, and as it gets more and more mass, it becomes a supermassive black hole, mass of billions of large stars, and everything around it starts to spin towards it and orbit it, and that's what happens. That's how galaxies generally form. So the actual supermassive black hole is thought to have been a key part of galaxy formation. It's what got the galaxy to take its shape in particular. So this type of black hole was first observed in 2016, which is, I don't know if you guys remember, it was like not that long ago now. And what had happened was two galaxies merged together, and as they merged together, the supermassive black holes at the core of each galaxy collided. As they collided, it produced loads of disruption in the actual curvature of space-time, and that disruption is called a gravitational wave. So we'll talk about gravitational gravity in general, and what a disruption in space-time could mean later. But however, what happened was this effect was able to be observed at Earth. It was done by a group called LIGO, which is an international collaboration, and they were able to actually look and measure this exact disruption. And in 2016, this was huge because not only did we finally know supermassive black holes exist, it was the first direct kind of irrefutable evidence that a black hole exists. Because in 1971, there was a lot of debate. But in 2016, it was, yep, that was what it was. Two black holes merged, and it completely fit the data perfectly. So now, even more excitingly, last April in 2019, they actually took a photograph of a black hole. So this is no artist representation, it's genuinely a photograph taken of a black hole. It was done by the Event Horizon Telescope collaboration. So in particular, what they did was they studied the energy coming from this part of the radiation coming from this part of the universe for a long time in infrared. And after a long time of processing the images, they actually formed it into this photograph. So a lot of people assume that they had a kind of telescopic camera and they took a photo, but it wasn't really like that. It was a reproduction of lots and lots of data. However, for sure, this is our first photograph of an actual black hole. It's the supermassive black hole in the galaxy M87. Okay, so in particular, what you're seeing at the center is the black hole, and what you're seeing the colorful kind of orbit is again just particles that have been supercharged kind of by spinning around the black hole so rapidly. Okay, so I'm going to pause again and ask if anyone has any questions.
Yeah, in the previous photo of the supermassive black hole, you said it was a center, but it looked really bright. Is that kind of like from the event horizon around it, or?
Yeah, that would be exactly it. You would be seeing kind of the event horizon, the highly energized area around it. The black hole kind of at the center would be much smaller in size than the amount of space it's taking up, that it's causing kind of these eruptions of energy. So that's what you usually see, a very bright center, really.
Okay.
Good. Okay, so I'm just going to take a quick pause before I move on to quantum mechanics and just give a quick history of gravity and space-time in general. So it all started with apples and Newton. Famously, an apple fell on his head. We don't know if this is actually accurate. And he decided that the way to explain this was that a force called gravity pulls all massive objects towards each other. It's an attractive force. And that was kind of how we understood gravity to work until basically 300 years later, when Einstein came along and he said, actually, no, let's think about it slightly differently. So what Einstein proposed was that gravity was not just a force pulling objects together or repelling objects with some mass. It was instead a fundamental property of space-time. In particular, the property it is the curvature of the space-time continuum. So instead of imagining us existing at 1:17 p.m. in this particular space in Ireland, what we should be picturing is we exist in a combination of this time and this space. They don't mean anything separately. So if somebody asks you where you are, you should be specifying your location as well as your time. The reason for this is because time behaves differently at different points in the universe. Okay? In particular, when you have a heavy object, such as the sun or the earth, what it does is it produces a dent in the space-time curvature. So the heavier the mass of the object, the more dense, the more curved the space-time curvature becomes. Okay? So in particular, if you go and you sit near the sun, less time would pass for you than would pass for me sitting over here on Earth. Okay? Time bends in such a way. So if you're there for, I should have earned some numbers. Okay, so actually a fun one to do is, if you think about Interstellar, the movie, and if you just kind of make a rough estimate that, so this is what theoretical physicists do, everything is rough, right? So let's just say theoretically, so the basic plot of the movie, for anyone who hasn't seen it, is there's some problem on Earth, no spoilers, I promise. There's a problem on Earth, and the dad goes and tries to sort it out by going near a black hole. His daughter is on Earth the whole time. He's gone for approximately about 5 years, but when he comes back, his daughter has aged 70 years. Okay, and this is for reasons such as so there's two things that bend the space-time continuum. One of them is if you're traveling very fast, in particular if you're traveling close to the speed of light. And then the second thing is if you're near a very massive object, such as a black hole or a star. So in particular, if you say he goes and he sits beside a star or a black hole for 5 years, then for him only 5 years would pass. But on Earth, time would run normally. It wouldn't be curved the way it is here, and 70 years would have passed. The science of the movie was all run through by an actual theoretical physicist, and it's genuinely, that is what would have happened if somebody was to go sit near a black hole for 5 years. So that in particular is general relativity. It sounds kind of weird, like quantum mechanics weird, but it's not. It's 100% not arguably, like it's 100% true. General relativity is fact. We've observed it tons of times. In particular, your phone is actually taking into account general relativity corrections every time it calculates its GPS, for example. So the GPS on your phone is getting data from a satellite sitting far away from the Earth. So time is passing by more slowly for them than it is for us. And that kind of correction over a year, for example, would give you an error of a couple of meters on your GPS. So your phone is actually taking it into account at all points. So general relativity, 100% true, completely observed. It started in 1916 by Einstein. He explained it. And now, I mean, we know it's true 100%. However, one of the interesting things actually just to say about black holes and general relativity is they are, if general relativity is correct, and we know it's correct, Roger Penrose showed, then black holes must exist, okay? So if this theory of particles, of how gravity behaves, of how massive objects behave, is correct, then black holes have to exist. Those strange looking objects from which nothing can escape have to exist 100%. For this particular calculation, Roger Penrose actually won the Nobel Prize yesterday. So I thought I'd include that in the slide. So in particular, coming back to our apple falling from the tree, what's actually happening is, so what you should picture instead is the space-time continuum. So I know it's hard to picture 4D. So instead, let's pretend this is my X direction and my Y direction, and my time direction is what's dipping. Okay, roughly just picture that for a second. The massive object is causing the time to kind of accelerate that way. So when the apple falls, so if you had a sheet of, like, so normally if we were in person, I would have brought in my scarf and usually an apple. But if I throw an apple onto my scarf, it'll cause a dip in the scarf. Okay. Now, if I was to throw something lighter, like a pen, on top of the same scarf, the pen would just roll towards the dip created by the apple. Okay, so that's actually what's happening with gravity. The Earth creates a dip in the space-time continuum. The apple creates a small dip. However, it's not really much smaller. I mean, it is much smaller, so it will just roll towards the Earth instead. And that's how gravity should be understood. So one of the things I just quickly want to say on this topic is just again, because of the chemists in the room, the reason he actually came up with this, that Albert Einstein started on this path of just being like, no, let's not go with gravity, the force. Gravity is more fundamental. And it all started with because, so when you look at forces normally, like the electromagnetic force, and you write out the formula F equals Q something divided by R square, or whatever the formula exactly is, I can't remember it off the top of my head. The proportion, the strength of the force depends on some constant, and that constant is to do with charge. However, and that force accelerates your body by m times the acceleration of the body, so ma, okay? However, gravitational force is, the formula for gravitational force between two objects is something like g times mm over r square. But the particular thing that determines kind of how strong the strength of gravity is, it's the same constant mass as the actual thing that causes the acceleration of your object. Okay, so in electromagnetism, for example, the force is determined by the charge of the particle, but how fast or slow it moves, or I mean the direction it changes, the speed of it changes according to the mass of the object. However, in gravity, both things are the same. The force's strength is governed by the mass, as well as how much the object actually accelerates is also governed by the mass. So the appearance of the mass on both those formulas made him think that maybe, you know, it's not right to think of the mass of a particle determining this force of gravity. It's more fundamental than that. The actual mass is what determines the acceleration. Why is it appearing twice? And this was his explanation, that it's not just a property of the object, it's a property of the space-time continuum. It's changing how the space-time continuum behaves, and that's what's causing the acceleration. And that's how we should view it instead. Okay, so before I move on to quantum mechanics, any quick questions about gravity? Okay, so quantum mechanics. So it explains the behavior of atoms and molecules. It forms the underlying rules of chemistry. So the size of orbitals and so on, it's all determined by studying quantum mechanics. In particular, the main thing about quantum mechanics and how it differs from general relativity is that it's completely based on probability. General relativity, although it's weird, still says the universe is deterministic 100% in nature. An apple falls off the tree onto the earth, it falls into the curvature of space-time, but it does fall 100%, and it follows an exact path. It's not going to do anything weird. It's going to fall straight down to the earth, towards the center of the earth. There's no doubt about that. However, in quantum mechanics, instead, everything is based on probability. So in particular, when you study atoms and molecules, so say I have two particles, and they're attracting each other through electromagnetism instead, let's go with. Okay, so my first particle is going to fall towards the second particle because it's more charged, let's say. Instead of going directly towards it, in quantum mechanics, it goes directly towards it as the most probable path it'll take. However, it could have also taken a very weird path and gone kind of around and gone up. It could have come here. It could have, in fact, traveled all around the universe and then arrived at the second particle instead. That's what quantum mechanics does. It's very unlikely it would have taken that path. However, there is a certain probability that it will. So that's kind of the fundamental thing in quantum mechanics and how it differs from general relativity. Everything is 100% based on probability. So in particular, there's the famous Schrodinger's cat experiment, which is a poison is put in a box with a cat, and the poison emits itself randomly. So quantum mechanics would tell you there's a probability it's emitted itself and a probability it hasn't. And oh, sorry, I should have added, in quantum mechanics, the probability of a particle going from here to here along a certain path becomes a certainty as soon as we observe which path it's taken. So the thing that changes quantum mechanics from a world of just probability clouds to an actual world that we see and observe is the fact that we actually observe it. So actual observation by a scientist or any human or any person, possibly even the cat, is what makes it a definite answer. What path it took, did the poison emit itself? So in particular, Schrodinger actually did not like quantum mechanics. So he actually designed this thought experiment to show the flaws in it. So he said, okay, so the poison may have emitted itself, it may not have, which means the cat is either dead in the box or the cat is alive. Okay. So until we open the box and look, so is the cat both dead and alive? Is there probability it's dead and probability it's alive? So what's actually going on in the box? So he was actually just ridiculing quantum mechanics. So there's just a little funny cartoon there anyway. This is kind of a quick overview of quantum mechanics, but what we need from quantum mechanics for the rest of this talk, I'm just going to say really quickly. So in quantum mechanics, there are two types of particles. You have your force-carrying particles, such as the photon in electromagnetism. It's the light particle. These are called bosons. Okay, and the second type of particles are your matter particles, called fermions. So your protons and electrons that make up your atoms and make you up and make me up. These massive particles are called fermions, and the force-carrying particles are called bosons. So there are two types of particles. And just one more time, I added, do not know how to unify this with a world of determined things like gravity. Excuse me, sorry, 1 second. Great. Okay, so a quick quantum process that we just need for the rest of this talk is just what's called a vacuum fluctuation too. So to explain it, let's start here. So in particular, suppose I have a particle, then I can also have an antiparticle. The antiparticle has the same mass as the particle. However, it has the exact opposite quantum numbers to the particle. So in particular, you have the electron, it has a certain mass, 10 to the minus 31 kilograms or so, and it's negatively charged. Its antiparticle pair is called a positron. It has the same mass, so 10 to the minus 31 kilograms. However, it'll be positively charged with the exact same amount of charge. So in particular, in quantum mechanics, every particle has an antiparticle. Okay. However, in quantum mechanics, just like in general relativity, just like in usual physics that we're used to, all processes must conserve mass/energy up to E equals mc squared. So you can't destroy and create mass slash energy. And similarly, all processes must conserve charge. Okay, so within quantum mechanics, you have two processes. The first one is called pair creation. Okay, this is when a force-carrying particle, boson, splits into a particle and antiparticle. The energy carried by the boson initially is equal to E, and it forms a particle of half m and using E equals mc squared, and the antiparticle would also have a mass of half m. So the energy before is E, and the energy after would be m over 2c squared times 2, so mc squared. Okay, so pair creation doesn't disagree with any of our presumed quantum processes conservation laws, such as charge, because the particle and antiparticle have opposite charge. It doesn't disagree with mass energy conservation because the energy of the boson goes into the energy of the particle and the antiparticle. Okay, you can also have the reverse process called pair annihilation. This is when a particle and an antiparticle collide together, they annihilate each other, and they produce a boson, a force-carrying particle. So I should have said force-carrying particles are not negatively or positively charged, they're neutral. So at the start, I have minus E for my electron charge, the antiparticle positron has charge plus E. Charge afterwards will be minus plus, so it'll give me 0, which is exactly the charge of a boson. Again, the mass of both of these particles will go into the energy of your boson. Okay, this photo here depicts a quantum fluctuation. So what's occurring here is a boson is just a force-carrying particle is just traveling across the universe. Over here, it splits into a particle here and an antiparticle here. Okay, so pair creates, the pair creation particle, the particles created run around this little loop and they annihilate each other. So your electron goes up here, let's say, it comes back, positron goes here and it comes back. They crash together in the middle and this antiparticle and particle collide, they annihilate and the boson just goes traveling. Okay. So in general, a vacuum is a region of space where there's no matter or energy. Heisenberg's uncertainty principle in general quantum mechanics say that you can't say for sure that a certain object or a certain system is a vacuum. You can't make certain statements in quantum mechanics. You can never say that box over there has 0 mass and 0 energy. So there's some error in the amount of energy even a vacuum has. And with that error, your particles can actually create and annihilate themselves. Okay, that photo is quite dizzying. In particular, vacuum, so an area devoid of space and of matter and energy, is actually full of particles being created from the boson borrowing its energy from the uncertainty principle. So the boson creates itself from the uncertainty principle. It pair creates a particle and antiparticle. However, they annihilate themselves, and then you get the boson back, and it returns its energy to the uncertainty principle. So before I view this box and after, before this process and after this process, the vacuum looks like a vacuum. Okay, no part of the process I don't violate the conservation of of charge. I do violate the conservation of energy mass, but that particular amount of energy that I'm violating is coming from the Heisenberg uncertainty principle. So overall, it's still allowed. So I keep telling you guys things for certain, like a vacuum is a vacuum, but in quantum mechanics, nothing is for sure. So in particular, a vacuum is not a vacuum either. It's full of particles just creating and annihilating themselves spontaneously. Okay, as weird as that sounds, before I move on to the slide, vacuum fluctuations are also known to be true, experimentally confirmed. What happens, the reason we know they're true is because if you run through the figures of, like, let's go with quantum electrodynamics, the theory that explains the quantum nature of electricity and magnetism, that theory will give you a certain mass of an electron, okay? However, when scientists go and measured the mass of an electron, they found a different answer to what we predicted. So the explanation lay in this vacuum fluctuation. The vacuum fluctuation gives a correction to the mass of the electron, and the exact correction it gives is the actual mass that we observe in the lab. So that actually is, in itself, it's proven that vacuum fluctuations must exist. Otherwise, and it's not just the mass of the electron, there's the mass of all fundamental particles gets corrected because of vacuum fluctuations, and the corrected mass is what we actually see in the lab. So yeah, empty space is just full of boxes, with particles just popping in and out of existence. So before I move on to the vacuum or quantum effects of black holes, are there any questions about that? I don't want to keep it on this, it's very distracting to look at. Let's keep it here. Any questions? Are people still with me?
Yeah, we're still here. Don't worry, Manya.
Okay. Am I going too fast or too slow or anything?
No. Yes, we're still here. It's just very interesting. I was going to ask, I'm a little uncertain whether I have a question or not. But I thought it was too much of a theory to be thinking about. But no, enjoying it.
Okay, that's great. I will finish up in like 5-10 minutes, which will leave us with 5-10 minutes, hopefully, for questions as well. Okay, so they're vacuum fluctuations. In particular, so we know gravity and black holes and all those exist. We know vacuum fluctuations exist for sure. So this is what Stephen Hawking is famous for. So when somebody asks you, why is Hawking famous? You can answer the question now. So what Stephen Hawking did was like, okay, well, these two things we know for certain. What if we imagine a vacuum fluctuation taking place near the event horizon of a black hole? Okay, so this is your black hole. The horizon is just its border, basically. It's the point of no return, as people like to say. So around it, there's some empty space. In that empty space, a particle creates itself and annihilates itself as it normally would over here. Okay, sorry, I should have said these pairs that are popping in and out of existence are called virtual pairs. Okay, so now Hawking said theoretically, what happens if this pair production annihilation happens close enough to the black hole that initially one particle falls in and the other particle is just about far enough from the center to escape? Okay, so let's just pretend the antiparticle falls in, and the particle is the one that gets to go away. Okay, so that's our little experiment. So let's study this with the few equations I will show you in this talk. So the first thing is, let the mass of the black hole be capital M, and let the mass of the particle and antiparticle be little m. Okay. The energy before the process, so my system is the black hole and the vacuum around it. The energy before is just the mass of the black hole times c squared. The energy after will be the mass of the black hole times c squared plus the particle that's escaped mass times c squared. Okay, big problem. We said that the conservation laws imply energy before and after any process must be the same. It must be conserved in any process. So how could we explain this? What could we say? Does anyone want to have a guess at how you could explain this? What could you do to correct this?
Would it be
EB equal EA? Sorry?
At the event horizon, you said two particles split, one go in and one escapes.
Yeah.
But it's an equal probability that the positive ones will go in and some negative ones will go in and balance each other out.
So they both have a certain mass, right? So the mass is just the mass.
Ah, yes,
right?
Sorry, yeah.
So it's a good thought, because some people actually use that as an explanation. They say that the antiparticle's mass should be taken as a minus m, and then they could balance each other out. So that's actually one of the interpretations. The one Hawking himself, though, decided on was in the process of the black hole eating a particle, it somehow loses some mass, and that mass is equal to the mass of the particle that ran away. Okay, so the energy after would actually be the mass of the black hole has decreased. So the mass of the black hole is now m minus little m c squared plus mc squared. Overall, adding them together, I'll get the energy before, which was just capital MC squared. So his explanation was that the particle lost mass. The black hole lost mass in this whole process. So this loss of mass or energy by the black hole is called Hawking radiation. In fact, it hasn't been observed yet. CERN are looking for it. We'll talk about that more in a minute. So I just want you to look at the experiment one more time. So this is one way of looking at it. Another way of looking at it is that a black hole is spontaneously emitting a particle of mass m. There's nothing wrong with that interpretation. In fact, you're seeing the same thing. You're seeing a black hole. It has mass capital M. Afterwards, it has mass m minus little m. And you're seeing a particle being thrown away, and that particle that's being thrown away has mass of little m. So the other way to think about it is that the black hole spontaneously emits particles. Now, a black hole spontaneously emitting particles doesn't agree with what a black hole is. We said nothing can escape a black hole. However, we say in quantum mechanics, nothing is for sure either. So there's a certain probability that your particle can escape the black hole, and therefore a particle will escape the black hole. And that's another way of looking at this whole process. The vacuum fluctuation one is the one you actually, that Hawking used to do calculations on what this could mean, what this radiation may look like. Okay, so he considers pair creation and annihilation near the horizon of a black hole and what this looks like for particles that are escaping. Okay, so through this process, black holes should be losing energy and mass over time. So at the start, I said nothing can escape a black hole. I'm telling you now, things escape black holes as well. In quantum mechanics, everything can happen, so why not? Now, the next thing that Hawking said, well, if black holes radiate, they will eventually lose all their mass and energy, and they'll eventually evaporate, okay? In particular, he calculated a formula which has the time taken for black holes to evaporate, okay? So this is the formula. I like to include this formula in my slide, even though it's a bit too much. The reason I like to include it is because it features all of the constants that we know in the universe. It has G, which is gravitational constant, that tells you how strong gravity is. It has the speed of light, that's another universal constant. It has Planck's constant, which deals with how large quantum effects are usually. So all of these quantum and gravity constants go together into this formula. So this black hole radiation is a true quantum gravity effect, okay? It's a quantum gravity process. We don't have a theory for quantum gravity, but by studying the limits of quantum mechanics and gravity and putting them together, we can actually say that there should be this thing within quantum gravity. So any consistent theory that one may form of quantum gravity should include black hole evaporation in it. Because we know it must exist. If the other two things exist, this must happen as well. So in particular, let's look at how long certain black holes take to evaporate. So if I had my primordial small black hole early universe, let's say its mass is 10 to the 11 kilograms. The evaporation time is 10 to the 9 years. For stellar black holes, the mass is 10 to the 32 kilograms, roughly, so about 10 times the mass of the sun. That's about 100 times the mass of the sun, actually. The evaporation time would be 10 to the 74 years, so 10 with 74 zeros after it, or 1 with 74 zeros after it. For a supermassive black hole of mass 10 to the 35, so a few 10,000 times the mass of the sun, the evaporation time would be 10 to the 82 years. So in particular, if you want to watch a black hole evaporate, we should take into account the universe is only 13 billion years old, 13.7 billion years old or so. 13.7 billion years, so that's about 10 to the 10 years old. So if a supermassive black hole formed on day one of the universe existing, although we know it didn't, it took a while anyway, but let's just pretend it did, then it would only be 10 to the 10 years old right now. It'll take this many years overall to actually evaporate. So supermassive black holes, I don't think we're going to see them evaporate in our lifetime. Same with stellar black holes, those numbers are way too high. However, for primordial black holes, there is some hope there, okay? So primordial black holes did form in the early universe, and they take 10 to the 9 years or so to evaporate, okay? So if it formed at the start of the universe, we might even see one evaporating if you were able to observe them somehow. So there's some possibility looking there. However, now really quickly, just the last thing I want to say is, so I said earlier CERN are looking for black holes. So how are they looking for black holes? What they're doing is they're smashing particles together, subatomic particles like protons and so on together, highly energized. So there's quite a lot of energy there. And one of the things they're actually looking for is that when they collide, a black hole, a small atomic-sized black hole, although the mass I've given here is much larger than an atomic-sized black hole, but let's go with it. let's say the mass of that black hole will be created. The mass of that black hole, let's just say, was 10 to the minus 5 kilogram. Then it would evaporate in only 10 to the minus 29 seconds. That's quite a short amount of time, but there's some hope of actually detecting this. So this is actually the kind of way CERN would be looking for black holes. In particular, not only would we be able to say then primordial black holes exist, we would also be able to say that black holes evaporate, which means they radiate, which means Hawking was correct, and this whole black hole radiation process, this quantum gravity process, is 100% observed and real, in fact. So this is kind of where I end my talk. So there's some hope there. You might ask 10 to the minus 29 seconds is not a long time to be around. That's 0.00 with 29 zeros and 1 second. However, that's still quite a bit of mass that it has to lose pretty quickly. It's quite a lot of mass that has to radiate very quickly. So what you would actually look for is that radiation signature instead. Okay, so that's everything from me. We've 10 minutes or so for questions. Thanks for listening. Do you have any questions?
Thank you.
That's right.
Hi, Manya. Thanks for the talk. It was really interesting. Can I just ask one question, please? Say just in, when you were talking about, say, time slowing down, when you're close to a black hole, like in the movie you mentioned, is there any way of predicting, say, the rate that time slows? How much does it slow by? And like, what does that depend on? Is that like dependent on the size of the black hole, or
Yeah. So there is an exact formula. I was thinking earlier on. I was like, oh, I should include that in the slide. But then I was like, oh, maybe it'll be too many formulas. Yeah. So there's an exact formula that you can use to calculate just exactly how much time would slow down by near different massive objects. So the conditions are that whatever is causing the time dilation has to have a certain amount of mass. So in particular, let me think if there's another interesting one. So it is something that we have to take into account even for satellites versus us. So time is passing by more quickly for us than a satellite away from the center of the Earth. So even that has to, that effect is even noticeable.
Sure, yeah.
Yeah. So yeah, there's an exact formula for it as well.
Okay, thank you.
No problem.
Manya, could I ask a question, please?
Yeah.
You mentioned that Stephen Hawking's got it wrong about the stellar black hole. Was he still alive when they found out the right answer, and what did he say?
Yeah, actually, so he was alive at the time. So I think actually it was done around 2016 when they first observed a black hole for sure, and that they were like, well, they exist. And by then there was actually no other theory that said a star should be shrinking in such a way, apart from the whole black hole model of a black hole devouring the star. I don't know what he actually said on it, but I do know. Okay, so look up the bet. It was between Stephen Hawking and I'm just trying to think the other physicist's name. It might come up with Stephen Hawking bet 1971 black hole, but he did pay up.
Very good, thanks.
I think it was with Roger Penrose, the bet.
What was it with Penrose? That would be interesting. Oops. Sorry. Any other questions?
I've two questions. Now have I forgotten them? Yeah, let me think. Well, I'll do the second one first. That's the one I can remember. My son was afraid when CERN was doing this experiment to form the black holes, that if they accidentally made one that was slightly larger, that it would start to gobble us all up. Is it possible?
No. So actually, I was running the numbers earlier on, just for like out of interest. So in general, the black hole that they'll form will only ever have enough mass or energy. So let's presume I smashed two protons together. So the mass of the black hole, let's presume all the energy of those photons or of those protons, as well as their mass, goes into creating the black hole. they won't even form a black hole that has a mass of 1 kilogram, let's say. But a black hole of mass 1 kilogram itself would evaporate in 10 to the minus 15 seconds. So like, it won't be around to do any harm.
Okay, thanks. I can put his mind at ease. So
exactly, like there's no way they'll create a large black hole because they never actually start with that much mass or energy anyway.
the other question was in relation to trying to detect the primordial black hole evaporating.
Yeah.
Have they any theory as to how they might observe one? Like, I mean, it's not going to be a bang or anything. It's just going to be there and then not there, I presume.
Yeah, so actually, unfortunately, I don't think they've had any luck in even observing the early universe before galaxies form. So I think the oldest kind of, so light travels at the speed of light. So if you want to look really, really far away, you're looking into kind of older structures in the universe. So the light coming from something that's billions of light years away is light that's billions of light years old. So you're actually looking at early universe in that case. However, the earliest photos we have are still way later than it would have been for primordial black holes. They still have structured, they're still, galaxies may not look beautiful in spiral, but they'll see galaxies in ellipses. So they haven't actually even got a way to look that far back when everything just exists in like what's actually called the quark gluon plasma. So it's when all particles just existed in a plasma state. The only way that they're hoping to actually observe that is by recreating similar conditions at CERN.
I see. Thanks very much. That was fascinating talk.
Oh, I'm glad.
Manya, if that's all the questions, I'd just like to say thank you so much on behalf of our staff development group. That was really fascinating.
Oh,
I'm glad it was recorded because I just felt I find myself going off thinking about something you said, and I'd go off on a track thinking about it, and then I'd come back and you'd have moved on. So I have to go back and have another look at things again. So thank you so much. It was very good.
Oh, that's good. I'm glad you enjoyed it. Yeah, everything in it is like a little fascinating subtopic. So it's like you could give a talk on any of the little topics within it for an hour instead, you know.
Yeah, that's true. You could. We might have to have you back again.
Thank you very much. Very, very interesting.
Glad you liked it. Thanks.
Thanks, Manya. Bye.
Thanks a million, Manya.
Thanks.
Bye.
Just before I go,